Let's examine the most intriguing category of splitting cores, the n+2 cores, which have 2 or more redundant dimensions. We can use them to split the original file very quickly if we use n+2 dimensions all at once, or we can freeze any dimension during the splitting procedure and the fission process will still work as expected, it will just take a bit more time. For illustration, consider this 4-dimensional 2+2 core which can split any file using either all 4 dimensions, 3 dimensions, or 2 dimensions of different colors, but it doesn't work if only one dimension is used, even if it is used several times. Okay, now let's be even more specific. Let's go through an example where we want to multidimensionalize and share a movie of size about 1 GB. For example, The Simpsons. First, we will cut the whole file vertically into 2 MB chunks. This is done mainly to take an advantage of today's CPUs and GPUs. This allows us to significantly speed up the splitting process by running it in parallel. We mark each 2 MB part at the beginning and at the end with a tag. Typically, this is done using our peer-to-peer network's license agreement. We then insert binary data into the data element, which usually takes up all 2 MB. The only exception is the last part of the file, which in most cases is smaller than 2 MB. For example, in the case of a video of size 893 MB, the last part is only 1 MB. But this is easily solved by inserting padding before and after the 1 MB of data. Finally, we optionally can encrypt the entire 2 MB piece using a symmetrical encryption algorithm. We use this procedure not only for copyrighted works but for all files that we want to share within the distributed data storage. In the first step, we use an innocent file, typically an endlessly repeated declaration of freedom of speech, and we split it. We have already gone through the splitting algorithm, so there is no need to explain it again. As the result, we will get 4 fragments of different colors, which the application will store in the cache. And now we can start splitting the original, most likely copyrighted file. We randomly select 2 fragments, for example red and white. Since these fragments are in the cache and they have not been compressed yet, we can use the transcript of the game directly by forgetting about which cards were drawn and just taking the numbers that were selected on the cards and XOR them with the first part of the original file. We then split the first part of the file and store green and blue fragments to the cache. After that, the whole procedure is repeated. We randomly select another 2 fragments, perform an XOR operation on the data and the second part of the original file, split the data and cache the result. The algorithm continues like this until the whole original file is properly multidimensionalized. There is one more thing worth of mentioning. For now, we have considered the situation where there are no fragments from other users stored on a disk. However, this doesn't happen in a real world. Typically, by the time when a user wants to upload their very first file to the distributed data storage, there will be, in the cache or on the hard drive, there will be some movies, games or books downloaded from other users. In that case, the user can entangle their files not only with their very own fragments, but also with fragments produced by other users. The idea is to select one fragment from the personal cache and one fragment that comes from foreign multidimensionalized file, then perform an XOR operation on it with the part of the file we are currently processing and split it. It is highly recommended to use the 3-4-3 rule, where at 30% we entangle to our own fragments, 40% of the time we entangle with one of our own fragments and one fragment from somebody else, and 30% of the time we entangle only to someone else's fragments. Here is a helpful tip to save time, effort and bandwidth. When entangling with fragments produced by somebody else, we should use such fragments twice or 3 times. By repeating this procedure, we can process a large number of files, creating a heap of fragments representing our own file system. This is shown here with the green background. The blue and orange backgrounds represent other file systems. Now, if you are paying attention, you might argue that splitting so many files using an n+2 core will create a lot of extra data, but that is not true. The magic of multidimensionalization is well illustrated in this image. The total size of all fragments is only a couple of percentage points, say 10% more than the aggregated size of original files. This is the price we have to pay to solve all the legal problems, including those related to copyright infringement. How is it possible? As you already know, every fragment starts with the declaration of freedom of speech and freedom of file sharing. Therefore, every fragment is by nature free and redistributable. And anybody can test this because every bit of every byte in a fragment reflects that declaration from the header of the file. On top of it, the payload of every fragment is a pure nonsense. It is a scramble of ones and zeros that means nothing. To reveal a meaningful information, the user must first decompress the data and then perform an XOR operation using fragments of the other three colors. But if you select a different three colors, for example these fragments, it will produce a completely different file. And here is the catch. The protocol says the red fragments can be shared only by computers with red IP addresses. Red IP address is the address where the hash of such IP address starts with binary numbers 00. Obviously, the green, blue, and alpha fragments are shared by computers where IP addresses start with 01, 10, and 11 respectively. And now you need to ask yourself, is user or probably many users sharing this red fragment breaking any law? The answer is no. Those guys are not doing anything wrong. They behave exactly according to constitution, and in most democratic countries this behavior is a kind of protected free speech. Imagine yourself as a copyright laws protector or law enforcement. You are very welcome to infiltrate this distributed peer-to-peer storage and you can download whatever you wish. But since everybody is publicly sharing only fragments which are of the same color as their IP addresses, then everybody is safe. You cannot stop this behavior. Also, anyone can take any fragment, mix it with copyrighted work or other digital data and publish it. This multidimensional data storage and protocol governing correct behavior is designed in a way that it is impossible to know who created the fragment, when it was created, and what kind of information is stored in it. It can be anything. It can be a photo of my cat, it can be a Linux distribution, it can be a copyrighted movie. Nobody knows. But everybody can check that the fragment was created properly and that it doesn't contain any meaningful information on its own. To be more precise, everybody can check that the fragment contains information in the state of superposition. Our distributed data storage has two major pillars: the logic behind multidimensional files and the zettabyte protocol. The logic behind multidimensional files ensures everybody is forced to split files into fragments using the proper setup of a fission core, or binary casino if you wish. Otherwise, the user will not follow the logic of the game, thus, he cannot store files to the distributed data storage. Zettabyte protocol is a set of network rules which every user should strictly follow to protect themselves and to check that nobody reveals any information which can be connected to any meaningful content. But now I'm getting a little ahead of myself. Before we describe the zettabyte protocol, let's talk about how to make a file system descriptor and how to share it with others.